For decades, astronomers believed this black hole had gone quiet forever. It sat hidden inside a distant galaxy, giving off almost no sign that it was alive. Telescopes scanned past it year after year. Researchers archived its data, labeled it inactive, and moved on to more exciting targets. Then, without warning, it woke up. Not slowly, not subtly. The darkness at the center of that galaxy suddenly erupted with an explosion of energy powerful enough to outshine billions of stars. Instruments across Earth and eventually in space began recording something that shouldn't have happened. A black hole that had appeared dormant for decades was feeding again. But what could possibly wake a sleeping monster? The answer would force astronomers to rethink one of the biggest assumptions about how supermassive black holes behave. Because the object at the center of this mystery wasn't just any black hole. It was one weighing millions of times the mass of our sun. And for reasons no one could explain, it had suddenly switched back on. At first, scientists wondered if their instruments were wrong. Black holes don't emit light themselves. Everything we know about them comes from the matter around them. Gas, dust, and unfortunate stars spiral inward, forming an intensely hot disk that glows brilliantly before disappearing forever beyond the event horizon. When that supply of material runs out, the brilliant glow fades. The black hole enters what astronomers call a quiet state. Not dead, just hungry. Many supermassive black holes spend thousands or even millions of years in these low-activity phases. Yet seeing one awaken within a human lifetime was almost unimaginable. Yet that is exactly what researchers began witnessing. The first clues appeared during routine sky surveys. Modern observatories no longer stare at just one object. Instead, they repeatedly photograph enormous portions of the sky, looking for anything that changes. Most changes turn out to be ordinary: a supernova, a variable star, an asteroid passing nearby. But this signal looked different. The galaxy had become dramatically brighter. Not by a few percent, not even by double. It had increased by dozens of times in brightness. Something enormous was happening deep inside its core. Naturally, scientists considered every possible explanation. Perhaps it was a supernova exploding near the center. Perhaps two neutron stars had collided. Maybe a hidden foreground object was distorting the measurements. Each possibility was tested. Each one failed. The light carried fingerprints. Every chemical element leaves unique patterns in light, known as spectral lines. These patterns revealed gas moving at incredible speeds, thousands of kilometers every second. Only one engine could produce conditions like that: a rapidly feeding supermassive black hole. But another puzzle immediately appeared. Historical observations showed almost nothing unusual decades beforehand. Old astronomical archives became treasure maps. Researchers searched through observations from ground-based telescopes, space telescopes, infrared surveys, ultraviolet records, radio observations, everything they could find. Piece by piece, they reconstructed the object's past. The evidence confirmed something astonishing. For decades, the black hole had remained almost completely inactive. Then, in only a matter of months, everything changed. Imagine walking past an abandoned factory every day for 30 years. No lights, no smoke, no workers. Then, one morning, every machine inside suddenly roars to life. The chimneys blaze, the building vibrates, the entire city notices. That is essentially what astronomers saw happening at the heart of this galaxy. But unlike a factory, no one could simply walk inside and inspect the machinery. The nearest explanation lay hundreds of millions of light years away. Scientists needed to solve the mystery only using light. But fortunately, light can tell extraordinary stories. Different wavelengths reveal different pieces of the puzzle. Visible light shows glowing gas. Infrared reveals warm dust. Ultraviolet exposes extreme temperatures. X-rays uncover the violent environments closest to the black hole itself. So observatories around the world coordinated their efforts. Each telescope became another detective interviewing the same cosmic suspect. Their combined evidence revealed something remarkable. Material wasn't merely falling inward, it was accelerating. The gas was heating to millions of degrees. Powerful radiation blasted outward. Magnetic fields twisted into enormous structures. The central engine had become violently active again. Yet one fundamental question remained unanswered. Where had all this material suddenly come from? Black holes cannot simply create food out of nothing. Something had to deliver enormous amounts of gas toward the galaxy's center. Several theories emerged. One suggested that two giant clouds of interstellar gas had collided. The collision may have robbed the gas of its orbital momentum, allowing gravity to pull it inward. Another proposed that gravitational disturbances from nearby stars slowly redirected matter toward the black hole over many years before reaching a tipping point. A third possibility involved something even more dramatic: a star, not just passing nearby, but wandering fatally close. If a star approaches a supermassive black hole too closely, gravity stretches it like spaghetti. Astronomers call this process spaghettification. Eventually, the star is ripped apart. Its gas forms a temporary feeding disk that shines brilliantly across the universe. These events are known as tidal disruption events. At first glance, this seemed like a perfect explanation. The sudden brightening, the enormous energy, the renewed feeding, everything fit. Almost. Except one detail refused to cooperate. Typical tidal disruption events fade relatively quickly. Months, sometimes a few years. But this black hole wasn't fading. It remained active, even years after its dramatic awakening. That meant astronomers were watching something fundamentally different. Perhaps the star hadn't simply been destroyed. Perhaps it had triggered something much larger. Attention shifted toward the accretion disk itself. This rotating disk is the true powerhouse surrounding a black hole. Matter within it crashes together. Friction converts gravitational energy into heat. Temperatures climb high enough to emit tremendous radiation. But accretion disks aren't stable. They can change, collapse, rebuild. Scientists had long predicted that these disks might undergo dramatic state changes. The mathematics allowed it. Computer simulations suggested it. Yet no one had ever clearly watched such a transformation happen in real time. Until now. If those models were correct, the disk may have existed all along, but in an unusually cold, dim state. Then, a relatively small disturbance could have triggered a runaway process. More heating, more radiation, more inflowing gas, more energy. Like pushing the first domino, the entire system would rapidly switch into a bright, active phase. It sounded elegant, perhaps too elegant, because new observations complicated everything again. X-ray telescopes detected violent fluctuations. The brightness wasn't steady, it pulsed, sometimes increasing dramatically, sometimes dropping unexpectedly. These weren't random flickers. They hinted that the environment near the event horizon was constantly changing. Extreme magnetic fields may have been reconnecting. Shock waves may have raced through the disk. Jets of energetic particles might have briefly formed before collapsing again. The black hole wasn't merely eating, it was struggling, as though the engine itself was stabilizing after years of silence. Meanwhile, another surprise emerged. Astronomers studying similar galaxies began discovering more objects behaving in comparable ways. One after another, apparently dormant galactic centers started showing unexpected activity. Had these awakenings always occurred, escaping detection because older telescopes lacked the sensitivity? Or was something larger happening across the universe? No one knew. But every new observation strengthened one conclusion. Dormant black holes were far less predictable than scientists had believed. The universe was revealing that these giants could switch between quiet and violent phases much faster than had been expected. That realization carried enormous consequences, because nearly every large galaxy, including our own, contains a supermassive black hole. If one distant galaxy could awaken almost overnight, could others? Could ours? The answer depended on understanding exactly what had triggered
The discovery of that tiny delay between different wavelengths of light transformed the entire investigation. Until then, astronomers had focused on one simple question: what suddenly fed the black hole? Now, a far more intriguing possibility emerged. Maybe the fuel had already been there all along. Maybe the real mystery wasn't the arrival of new material. Maybe it was the sudden restart of the engine itself. To understand why that idea was so revolutionary, imagine a campfire that appears almost extinguished. The wood is still there, the ashes remain warm, only a few hidden embers survive beneath the surface. A small gust of oxygen arrives. Within minutes, flames return. The fuel never disappeared, only the conditions changed. Researchers began wondering whether something similar had happened around this supermassive black hole. For years, the accretion disk may have contained enormous amounts of cold gas orbiting safely around the event horizon. Instead of glowing brilliantly, that gas remained relatively cool and inefficient in converting gravitational energy into radiation. To distant telescopes, the black hole looked asleep. But beneath that calm appearance, the system may have been quietly preparing for a dramatic transition. Then, at some critical moment, everything shifted. Computer simulations have long suggested that accretion disks can become unstable under the right conditions. As material slowly accumulates, pressure increases, temperatures rise, magnetic fields become tangled. Eventually, a tipping point is reached. The disk suddenly changes state. Instead of transporting matter inward slowly, it begins funneling enormous amounts of gas toward the black hole. The entire system brightens dramatically. This process is sometimes compared to flipping a switch, except the switch controls an engine capable of releasing more energy than entire galaxies. The delayed light observed by astronomers fit this scenario surprisingly well. Ultraviolet light increased first, visible light followed, infrared radiation appeared later. That sequence suggested heat was spreading outward through the disk rather than appearing everywhere at once, exactly as theoretical models predicted. For the first time, scientists weren't merely studying a bright active galaxy, they were watching the birth of one. The object had effectively changed classification during a human lifetime. For decades, it resembled a quiet galaxy with an inactive nucleus. Now it behaved like a ciphered galaxy, a class of galaxies powered by actively feeding supermassive black holes. For generations, astronomers assumed these categories represented stages lasting hundreds of thousands or even millions of years. This object suggested the transformation could occur within months. That realization shocked the astronomical community. If galaxies could change this quickly, then our understanding of galactic evolution required serious revision. Suddenly, old survey data became more valuable than ever before. Researchers returned to decades of archived observations. Instead of asking which galaxies were active, they asked a different question. Which quiet galaxies had become a little brighter over time? The search uncovered more surprises. Several galaxies showed subtle warning signs years before their dramatic awakenings. Small increases in ultraviolet light, gradual changes in emission lines, tiny fluctuations in brightness that previously seemed unimportant. In hindsight, these were early whispers of much larger events. Astronomy entered a new era. Instead of discovering awakenings after they happened, scientists hoped to predict them before they reached full intensity. At the same time, space-based X-ray observatories continued monitoring the mysterious object. The region closest to the event horizon produced violent bursts of high-energy radiation. Some lasted only hours, others persisted for days. These rapid variations revealed something extraordinary. The brightest regions were incredibly compact. Light itself could cross them in only a short time. That meant the activity originated astonishingly close to the black hole's event horizon, only a few times larger than the point of no return. General relativity predicts that space and time become profoundly distorted in this region. Gravity bends light, time slows, matter follows paths impossible to imagine under ordinary conditions. Every fluctuation carried clues about physics operating in one of the most extreme environments in the universe. Magnetic fields appeared to play a crucial role. Near the event horizon, magnetic lines twist and stretch as hot plasma rotates at enormous speeds. Sometimes those fields snap and reconnect in explosive events similar to solar flares, but incomparably more powerful. Each reconnection releases tremendous energy. Particles accelerate close to the speed of light. X-rays flood into space. Some of that radiation illuminates the surrounding accretion disk. The disk reflects part of the signal back towards Earth. By measuring these tiny echoes, scientists can estimate the geometry of regions they will never directly see. It is an astonishing technique. Scientists use light bouncing around invisible structures surrounding an invisible object to map a place no telescope can resolve directly. The awakening became more than an isolated curiosity. It evolved into one of the best laboratories ever discovered for studying supermassive black holes in real time. Every month produced new observations. Every observation refined theoretical models. Yet the mystery wasn't completely solved. No single explanation accounted for every feature. Some evidence supported disk instability. Other measurements hinted that fresh gas had recently reached the nucleus. A partial tidal disruption of a star remained possible. Perhaps multiple mechanisms worked together. A slowly accumulating reservoir of gas, a passing star disturbing the system, magnetic instabilities triggering runaway heating. Nature rarely follows the simplest storyline. Instead, it often combines several processes into one breathtaking event. That possibility actually excites astronomers because reality is usually richer than our first theories. Meanwhile, the implications extended far beyond one distant galaxy. At the center of the Milky Way lies Sagittarius A star, the supermassive black hole around which our entire galaxy revolves. Today, Sagittarius A star is relatively quiet. Compared with actively feeding galactic nuclei, it emits surprisingly little radiation, but evidence suggests it has not always been so peaceful. Gigantic structures known as the Fermi bubbles rise tens of thousands of light years above and below our galaxy. Many researchers believe these enormous features were created by a much more active Sagittarius A star millions of years ago. Our own galactic center appears to have experienced periods of awakening and dormancy. The distant black hole reminded scientists that inactivity does not mean permanence. A quiet giant may simply be waiting for the right conditions. Fortunately, there is no evidence that Sagittarius A star is preparing for a dramatic outburst anytime soon. Even if it eventually became more active, Earth is safely located about 26,000 light-years away. The event would provide spectacular science, not immediate danger. Still, the comparison carried a profound message. Black holes are not static monsters frozen in time. They are dynamic engines responding to their environments. Galaxies and black holes evolve together. Gas flows inward, stars are born,
Stars die. Gravity reshapes everything. The central black hole participates in that story across billions of years. The awakening also highlighted the extraordinary progress of modern astronomy. Just a few decades ago, an event like this might have gone completely unnoticed. Today, automated sky surveys repeatedly scan the heavens every night. Artificial intelligence helps identify unusual changes almost immediately. Ground-based observatories coordinate with space telescopes across multiple wavelengths. Within hours of detecting something unusual, astronomers around the world can begin observing the same target. This global network transformed one unexpected brightening into one of the most intensely studied black hole events ever recorded. Perhaps the most remarkable lesson is philosophical rather than technical. The universe often appears calm simply because we observe it for such a short time. Human civilization spans only a tiny fraction of cosmic history. Processes that seem permanent may actually be temporary pauses. Mountains rise and erode, stars ignite and fade, galaxies collide, black holes awaken. Our perspective determines what feels eternal. The black hole had not truly been asleep forever. It had merely paused during the brief moment humanity happened to be watching. Somewhere tonight, countless other supermassive black holes are quietly waiting. Most will remain dormant for thousands of years. Some may awaken tomorrow. Others may already be changing, their first faint signals racing across intergalactic space towards Earth. Those photons could arrive next week, next year,